Algebra 2 course, Lesson 10, Solving Systems of Equations by Graphing. In this lesson we will cover quite a few things. We will first go over the definition of a system of equations. Secondly, we will discuss the three possible outcomes to systems of equations. And finally, we will solve systems of equations by graphing. And when graphing, we will at the very end of the lesson show the use of graphing calculators to solve by graphing, specifically the TI84 Plus calculator and the TI-Nspire calculator. First, we'll ask the question, what is a system of equations? The simple answer is that it's at least two equations with the same variables. And one more distinction. In this lesson, we're talking about systems of linear equations. Later in the course, we'll look at systems involving different types of equations, but here in our course, this lesson, we're looking at lines, building from the recent lessons on finding equations of lines, graphing lines, etc. Let's look at what could be a real-world problem. Megan wants to buy a coat that costs $100. If she saves $10 per week from her job earnings, how long will it take her to save the money to buy the coat? Here's another system of equations situation. John walked to his mother's house in an hour and a half. If John walked at an average speed of 3 miles per hour, how far did he walk to get to his mother's house? In these two problems, the numbers are such that the answers should be pretty easy, but they are really both systems of equations. The purpose of these two examples is to show that you are already familiar with systems of equations from everyday life. So conceptually, it shouldn't be too difficult to understand. Now we'll briefly discuss possibilities when looking at systems of equations. The first possibility is the one that happens most often, that there is one place where two lines intersect on a coordinate plane. That means that there is one solution to these types of systems of equations. And in any system of equations with one solution, there is an important point where the lines intersect. And this is the solution to this system, point 1, -1. There are different ways we can tell if a system of equations has one solution, if the lines have different slopes, or we can see where the lines cross, or even see that the lines will cross at some point on the coordinate plane. We know the system of equations has one solution. Another way of describing this possibility is that in this type of system, the lines are consistent and independent. That's the language some textbooks use for this situation. Another possibility is where there is no solution to the system of equations, where the two lines are parallel and do not intersect. We can tell that there is no solution if the two lines are parallel, or if their slopes are the same and their y-intercepts different. It is also said that this is a system of equations that is inconsistent. And finally, there is a third possibility, and that is where there is an infinite number of solutions. This is one line on top of another such that they both occupy the same line in the coordinate plane. Graphically, drawing two lines as one is difficult to do, and I've done it here in this graphic by putting the red line so close to the blue line that there is no space between them. In equations of a line, two equations can be in different forms so that the equations look different, but they are really all of the same line. We call this a situation where the lines are consistent and dependent. In the world of finance and human behavior, there is a tool to help economists find the optimal quantity and price of a certain product or commodity. Those of you going into business school will use this tool to evaluate this relationship, and these are called supply and demand curves. The demand represented by the blue line has a negative slope because the higher price the product or commodity, the less there will be of a demand. And for the supply represented by the red line, the greater the price, the greater the supply of that product will have as more producers are willing to sell as the price of an item goes up. This point, the intersection of the supply and demand lines, is the optimal amount of production to satisfy both producers and consumers. This is a real-world use of a system of equations. Let's talk about an intersection. Let's say that you're standing at the intersection of two streets, Main Street and Elm Street. What would that mean? It means you're in danger of getting run over if you don't move. But seriously, what it really means is that when you stand in the intersection of Elm and Main Streets, you are standing in two different streets at the same time. And getting back to our supply and demand graph, the intersection of supply and demand is the one place that these two lines have in common, just like our intersection of the two streets. We call this point the solution to a system of equations. One thing we talked about during the introductory lesson was the importance of a particular point of intersection in business, what is called the break-even point. Joe has a business selling snow cones. If his equipment costs are $10 per day and his material costs per cone are 50 cents, how many cones must he sell at $2 each before making a profit in a day? The red line represents Joe's cost per day as a function of sales, and the blue line represents revenue from sales. And this point where the two lines intersect gives the answer to the problem. It looks to be about 7 cones sold before earning a profit, and that would be about $13 in sales in a day. So we'll call this point the coordinate 7, 13. If you ever have a business, this is the number you are highly interested in. This is a real-world application of using systems of equations. Let's look at this system of equations. We have y equals 3x minus 3 and y equals 2x plus 1. At this stage of the lesson, I invite the viewer to stop the video and get out a pencil, ruler, and graph paper to follow along. Here's the coordinate grid on which we'll be graphing. We'll take the first function, y equals 3x minus 3, and mark its y-intercept at -3. And with a slope of 3, we have a rise of 3 from the y-intercept, so we go up 3 units. And then we have a run of 1, so we go to the right 1 from the end of the rise. Then we place another point at the end of the run. And for drawing accuracy, we draw in another rise over run of 3 over 1. And here's our ruler to line up the points. And here's the line drawn in with the line labeled. Now we'll draw in the second line, and we start with the y-intercept of 1. From here we have a rise of 2 with the slope being 2. And then we go to the right with a run of 1. And now we place a point at the end of the rise and the run. We can get another point for accuracy by repeating the rise over run along with another point. We get out the ruler again. We line up the points as well as we can. Now we draw in our line with the line labeled. And we see the convergence of the lines here. This is our intersection or solution. We mark and label the point as the coordinate 4, 9. And after solving, we will do one last thing, check our answer. Here's the first equation with 4, 9 plugged in for the x and y values, and that's 9 equals 3 times 4 minus 3. That simplifies to 9 equals 12 minus 3, which comes to 9 equals 9, check. Now we use the second equation to check. We have 9 equals 2 times 4 plus 1, and that becomes 9 equals 8 plus 1, and that becomes 9 equals 9, check. Here we have another system of equations to solve. We have y equals 2x plus 2 and 4x minus 5y equals 20. The first equation, y equals 2x plus 2, can be graphed by first going to the y-intercept of 2, and using the rise over run of 2 over 1, we get this second point. Then we can mark a third point for accuracy. Then draw a line through the points. Now on to the graphing of that second linear equation, 4x minus 5y equals 20. To graph this, we could do it at least a couple different ways. We could solve for y and convert to the slope-intercept form. We could also use the intercept-intercept method, which is quite easy to use for equations in standard form, and that's what we'll do here. First, we'll find the x-intercept by setting y equal to 0, and I do this by covering up the y term with my thumb. That leaves us with 4x equals 20. And dividing by 4, that is x equals 5. And so we mark the x-intercept at 5. Now we'll find the y-intercept by covering up the x term. And that gives us negative 5y equals 20. And solving for the y-intercept, we divide by negative 5 and get y equals negative 4. And we mark the y-intercept at negative 4. Then we draw the line connecting the two intercepts and label the line with the equation 4x minus 5y equals 20. We locate the intersection, our solution, here in the third quadrant, and this coordinate pair appears to be the point negative 5, negative 8. And now we'll perform the check of each equation using our solution, -5, -8. Using the first equation, we have -8 equals 2 times -5 plus 2. And that simplifies to -8 equals -10 plus 2. And that becomes -8 equals -8, check. Now we continue our check of the solution using the other equation. That is 4 times -5 minus 5 times -8 equals 20. That becomes -20 plus 40 equals 20. And this becomes 20 equals 20, check. We verified that -5, -8 is the correct solution. In solving by graphing, it is important to check because drawing lines can be prone to the error of lines not being in the exact location they should be. Here's another system of equations problem. Y equals -3/4 x plus 6 and 6x plus 8y equals 48. For this one, we'll mark the y-intercept of the first equation at y equals 6. And now we take the rise of -3, and so that's down 3, and then we use a run of 4. Then we mark the second point. Now for accuracy of the drawing, we can use the rise and run a second time to get a third point. And using the points, we can draw the line and label it with the equation. For the second equation, we find the y-intercept by covering up the x term, so we have 8y equals 48. And dividing by 8, we have y equals 6, or a y-intercept of 6. And as we mark the y-intercept, we notice that it's in the same as the y-intercept of the first equation. In finding the x-intercept, we have 6x equals 48. And dividing by 6, our x-intercept is 8. And marking the x-intercept, we see it's the same as the x-intercept of the first equation. So the second line goes on top of the first line. So the solution to this system of equations is infinite solutions. Every solution is common to both lines. Another way we could have detected the result of infinite solutions is to solve the second equation for y. And we'll do that here. The first thing we do is subtract 6x from both sides of the equation. 6x minus 6x cancel on the left side to equal 0. We bring down what's left. 8y equals 48 minus 6x. Divide both sides of the equation by 8. 8 over 8 cancel on the left side to equal 1. We bring down what's left, and it's y equals 6 minus 3/4 x. And at this point, we should be able to see these two equations as the same, again showing that this system of equations contains an infinite number of solutions. Let's look at this system of equations. We have y equals 3x minus 2 and y equals -x minus 6. And for this one, I invite the viewer to pause the video and then work ahead to see if you got it. Here's the first equation, y equals 3x minus 2 graphed. Here's the other equation, y equals -x minus 6. And our solution, or intersection, is found at -1, -5. It's this point that these two lines have in common. And finally, the check of the solution. Here's the check using the first equation, check. And here's the check of the solution using the second equation, and it also works out, check. Here's another system problem. We have 2x minus 3y equals 6 and x plus y equals -12. For this problem, I again invite you to pause the video and work it out, then restart it, see if you got it right. Here are the two equations graphed. The one with the positive slope is 2x minus 3y equals 6, and the one with the negative slope is x plus y equals -12. And the intersection is here at -6, -6. And testing the solutions in both equations, we see that they both do check out. Check. We'll look at solving a word problem by graphing. Yvette is now 4 years younger than her brother Xavier. In 10 years from now, she will be twice his age today. What are their ages today? The first sentence translates to y equals x minus 4, which is based on their ages today. The second equation is y plus 10 equals 2x, which is based on their ages 10 years from now. Here a grid is provided. I invite you to pause the video, see if you can solve this system by graphing. Here's the graph of y equals x minus 4. And added to that here is the graph of y plus 10 equals 2x. And the two lines intersect at this point, 6, 2. And the answers are that Xavier is 6 years old and Yvette is 2 years old. Now to test the solution, they both work. Check. Towards the beginning of the lesson, we had this problem about Megan saving to buy a coat. Even though it's a pretty easy problem that could be solved without graphing, I want to show why it's a system of equations that can be solved by graphing. The equation for Megan's savings is y equals 10x, as in the money she saves is found by calculating the number of weeks and then multiplying that by 10. And then the equation y equals 100, as in the $100 Megan needs to save. And the place these lines intersect is here at the point 10, 100. So the answer to the question is 10 weeks. Megan will have saved $100 after 10 weeks. Here's another system of equations we looked at about John walking to his mother's house. Here the coordinate grid is prepared for graphing. The first equation we'll look at is this one, 3 miles per hour. We call it d equals 3h. And we also have the time it takes, an hour and a half. That equation is h equals 1.5. First we'll graph the line h equals 1.5. It's a vertical line halfway between h equals 1 and h equals 2. Now we have the line d equals 3h. With a y-intercept of 0, we mark the starting point at the origin. And with a rise over run of 3 over 1, we rise 3 units from the origin, and we have a run of 1. And we mark our second point at the end of the run. Then we can draw the line of the equation through the 2 points. And this is our intersection point at 1.5, 4.5. So our answer to the question is 4 1/2, or 4.5 miles. Now we'll take an abrupt turn in our lesson and work with graphing calculators. We'll use both the TI84 Plus and the TI-Nspire calculators. You may be a purist mathematician who doesn't like to use calculators, if you can help it, or maybe you're someone who just wants to be able to do things without calculators, and that's fine. But I think it useful to show how this technology that is available all over the world can help us. It can help us first in graphing systems with very large numbers, such as this system we can use to find the side lengths of a rectangle. It also helps us if the solutions are non-integer or non-whole number answers. It helps if we need to do a sensitivity analysis. A sensitivity analysis is where we look at how changes in factors will affect the problem. With the graphing calculator, this sensitivity analysis is very quick. And finally, when drawing lines, it's easy to make errors. Having two lines, both of which can be inaccurate, can compound human error. There's even error due to drawing line thickness, which using the graphing calculator will eliminate. I'm going to start out using the TI84 Plus calculator. This will be the same for all TI83 and TI84 series calculators. If you're using the TI-Nspire, I'll be doing the same problems at the very end of this lesson, but instead using the TI-Nspire, so you might want to move the video ahead to get the TI-Nspire portion of the video. First problem, solve the following system of equations. We have y equals 2x plus 1 and x plus y equals 4. We first access the function editor of the graphing calculator by pressing the y equals key at the upper left of the keypad. We then enter the first equation, y equals 2x plus 1. Then we enter the next equation, and we start by entering a 4. And then we have to finish entering the equation, and to do that we have to solve for y. So we subtract x from 4, which is really subtracting x from both sides of the equation to get y by itself in slope-intercept form. Next we graph by pressing the graph key at the upper right of the keypad. If the view screen window is messed up, press zoom then 6 to get a standard window. Here is the intersection or solution. If we see it like we do here on the view screen, it's easy to evaluate. Press the second key at the upper left of the keypad, press trace, press 5, press enter again, press enter one last time. And we're now given the calculation of the intersection or solution at 1, 3. Let's look at this system of equations with both equations in standard form. We have 5x plus 9y equals 112, and we have 3x minus 2y equals 8. First thing, press the y equals key at the upper left of the keypad. Next, open parentheses. Then enter the number of the first equation, 112. We have to solve for y on the left side, so what do we need to do that's the opposite of the positive 5x on the left side? Subtract 5x. Now close parentheses. Next, to finally solve for y, we need to divide by the coefficient of y, which is 9. Press divide. Now we enter the coefficient of y, which is 9. On the next line, we start the same process with the second equation. Enter open parentheses. Next, enter 8. Next, we subtract 3x. Close parentheses, and then we divide by the coefficient of y, which is negative 2. Next, press graph at the upper right. We see the intersection or solution. We find what that solution is by pressing second, press trace, press 5 for the intersection, press enter a second time, and press enter a third time. And we see that the coordinates of our solution are at 8, 8. I promise you that I checked the solution in both equations and the solution is correct. Here we have another system of equations. We have y equals 5x minus 6 and 10x minus 2y equals 20. One equation is in slope-intercept form and one is in standard form. I want you to watch carefully because it's a special situation. First we enter 5x minus y in y1, so we have the first equation entered. Next we enter the second equation by opening parentheses, entering 20, subtracting 10x, closing parentheses, then dividing by the coefficient of y, which is negative 2. Press graph. We have two lines, which appear to be two parallel lines, and if they really are parallel, there is no solution to this system of equations. When I see something like this, where I go to be sure is to the table view. Press second, press graph at the upper right of the keypad, which gives us the table view. We know for sure in examining because we see all the y1s and y2s 4 units apart. Here's a word problem we'll solve as a system of equations. A rectangle whose perimeter is 90 centimeters has a length 3 times its width. What are the dimensions of the rectangle? One equation involves the perimeter and is 2L plus 2W equals 90. And the other equation is L equals 3W. In y1 we can place 3x. We will have to use x and y as variables in place of W and L, or length and width. To enter the second equation we enter parentheses 90 minus 2x, close parentheses, divided by 2. Press graph. Only one line is visible. Go to Window to adjust to be able to see both lines. This is the default window with the standard calculator settings. We know that the perimeter is 90, so half that should be great enough to cover the possible dimensions of the rectangle. Set x max and y max to 45. Press graph. We can see the intersection or solution. We can get it by pressing second, press trace, press 5 for the intersection, press enter, then enter again, and enter one last time. Here we see the intersection or solution, and the rectangle has a width of 11.25 centimeters and a length of 33.75 centimeters. This problem would have been tough to do accurately by graphing using graph paper. Now we'll do the same problems using the TI-Nspire. First problem, solve the following system of equations. We have y equals 2x plus 1 and x plus y equals 4. When we press the home key at the upper right, this is the menu we get. Scroll down so the graph icon at the bottom is enlarged. This is the second item from the left on the bottom row of icons. Press enter, or the center of the touchpad. Enter 2x plus 1. Scroll down to f2 of x. In f2 of x, enter 4 minus x, which is the equation solved for y. Press enter. We see the intersection or solution where the red and green lines cross. To find the solution, go to Menu. Here's option 6, Analyze Graph. Press 6. Look at option 4, Intersection. Press 4. Lower bound question mark is shown in the lower left. Now it says upper bound. Using the touchpad, scroll to the right of the intersection. You can see the grayed out area going to the right. And if you look hard, you can see a grayed out coordinate pair below the intersection label. Press Enter. It shows the intersection or solution at 1, 3. Let's look at this system of equations with both equations in standard form. We have 5x plus 9y equals 112, and we have 3x minus 2y equals 8. Get a new graph page. You can go to New Document and it will ask you if you want to save. I usually say no. We enter the first equation by opening with parentheses. Inside parentheses, we enter 112 minus 5x, then divide the expression inside parentheses by the coefficient of y, which is 9. Scroll down to f2 of x. Enter the second equation in the same manner. Enter quantity 8 minus 3x divided by negative 2. Press Enter. To see the first line, we need to change the window settings. Go to Menu, then 4, which is Window Zoom. Press Enter to get option 1, Window Settings. I'll change Y max to 10. Tab down to OK, then press Enter. Now we see the intersection or solution in the upper right corner. Find the intersection by going to the menu, Analyze Graph, press 4 for intersection. Set the lower bound, press Enter. Set the upper bound, press Enter. We have an intersection at the point 8, 8. Here we have another system of equations. We have y equals 5x minus 6 and 10x minus 2y equals 20. One equation in slope-intercept form and one in standard form. I want you to watch carefully because it's a special situation. We get another graph page and enter f1 of x equals 5x minus 6. We enter the second equation by scrolling down to f2 of x and entering f2 of x equals quantity 20 minus 10x divided by the coefficient of y, which is negative 2. Press Enter. As a result of graphing, we see two parallel lines, or lines that appear to be parallel. If they are parallel, there is no solution to this system of equations. But we'll take another look using the table view. To get to the table view, press the Control key labeled CTRL, then press T for Table. We see the output values in the table 4 units apart, verifying that the two lines will never touch. There is no solution. Here's a word problem we'll solve in a system of equations. A rectangle whose perimeter is 90 centimeters has length 3 times its width. What are the dimensions of the rectangle? One equation involves the perimeter and is 2L plus 2W equals 90. And the other equation is L equals 3W. We get another graph page and enter f1 of x equals 3x. Scroll down to f2 of x and enter quantity 90 minus 2x divided by 2. Press Enter. We see only f1 of x equals 3x. To see the other equation as well, we need to adjust the window. Go to Menu and Window Zoom. Press Enter for window settings. We need to change these window settings to be able to see the intersection. Since the perimeter of the rectangle is 90, let's allow for enough length and width by setting x max to 45 and y max to 45 as well. Scroll down to OK, then press Enter. We now see the intersection, which is the solution. Go to Menu, Analyze Graph, choose 4 for intersection. Use the touchpad to set the lower and upper bounds, then press Enter. We get a solution of 11.3, 33.8, which means that the width of the rectangle is 11.3 centimeters and the length is 33.8 centimeters. Again, that's rounded from what we saw earlier if you watched the TI84 Plus version. We've covered quite a bit in this lesson. We've graphed systems of equations in standard form, slope-intercept form, and using graphing calculators. In Lesson 11, we'll start on algebraic methods of finding solutions to systems of equations, and the first one we'll do is solving systems by substitution. This has been Algebra 2 Course Lesson 10, Solving Systems of Equations by Graphing. Thanks for viewing.